Because it's recording. Let me hide some things. All right, there we go. So happy. Oh yeah, you can still send emails and stuff. If you have questions, definitely send emails and things. You absolutely can do that. This needs to just go away. I don't know how to get rid of this. I don't know. Okay, so you definitely still send emails. I will be answering questions and all of that. Graduation is from about 6 to 7:30 or 8ish, whatever. So anything sent to me before about 5 on Thursday, I'll be able to answer. And then obviously Friday, I'll still answer emails and my normal answering them as much as I can throughout the week. So yes, definitely send me things. This is just tonight is the last of the new material you'll be learning. And then we have our test next week. We have tests next week. And then the week after that is the final project due. So we are almost done. I mean, we're so close to done. This is week 9. So including this week, we have 9, 10, and 11. So basically 3 weeks, but I mean, the last week you submit everything on Tuesday, and then the rest of it is just looking at everybody else's great stuff and leaving them meaningful comments. So that part's fun. It is super fun to look at other people's things. So we're doing chapter 10 today. So 10.1 is kind of like the vocabulary part. We're going to talk about what a null hypothesis and an alternative hypothesis is. We're going to talk about type 1 and type 2 errors, and then show you what a conclusion of a hypothesis test is. 10.2, we will talk about how we test a hypothesis, and then we will do testing on population proportions. So it'll be using some of the stuff that we did in 8.2, sorry, and 9.2, and we'll be extending that a little bit with hypothesis testing. 10.3 is things we did in 9.1 and 8.2. We're going to talk about means and do those types of hypothesis testing. Now, if you look at the number of slides we have, don't do that. It looks like a lot. Most of them we flip through pretty quickly. So it's not as much as it seems. It's really not that terrible. All right, grab my iPad. The nice thing also about this new computer is it has this fancy charger so that it's going to hold a charge better. So if I end up doing that dumb thing again that I did where I didn't have it plugged in and the battery was really low, it'll still charge it and hold a charge. It has a fancy, I don't know, like magnetic thing. I don't know. It's really kind of cool. So let's get started. Is the MacBook worth the money? I would say the MacBook is not worth the money, in my opinion. My PC does just as good of a job, if not better, and it costs like half, maybe not quite half as much, but a little more than half as much. And I'm not really a big Apple girl, even though I do have an iPhone and I have an Apple Watch. I do love my Apple Watch, which is why I have an iPhone. Yeah, so for the question is, yeah, the school gave me the MacBook, otherwise I probably wouldn't do it. So with the question in comment says, for writing on the final project, it says handwrite one calculation. Could I do something like handwrite and upload it? Yes, that's fine. Or you can type it in. Either way, a lot of people will they will scan it or take a screenshot of it and then just paste that, like snip it and paste it into their paper. That's fine. Or if you want to type it in Word, that's fine also. Either way, for your for the one hand calculated thing. So either way is perfectly fine. All right. So let's get started. Okay, so what a hypothesis is, it's a statement regarding a characteristic of one or more populations. So we might say something like, you might say something like, I think, so someone's told me that the average percent of people that own their home is 25%. And your hypothesis could be that you think that the number is actually different than that. So it could be higher, it could be lower, but you don't think it's 25%. That could be a hypothesis. Or if you hypothesize that it is larger than that, or you hypothesize that it's lower than that. You don't yet have your evidence. You're making a statement, and then you will gather your evidence. We are not going to be comparing populations here. We're just going to look at a single population parameter. So we're not going to be comparing things. That would be 244. If you take stats 244, then that would be the comparing the populations. Or if you decide to do hypothesis testing with two different populations to get extra credit, you can move forward in your book. I don't know what chapter it is, but you can look forward in your book. So for the extra credit for your final project, you basically need to teach yourself something. And I've had a couple of people do it before, but so basically you teach yourself something. You can go to a different chapter in the book and teach yourself something. All right. So if you printed off the PowerPoint, I did delete a few of the slides. So just letting you know. So if we're testing a hypothesis, we would take sample evidence and we would determine the probability that that evidence happens using what we're given. So for example, the 25% people owning the houses. So if 25% of all of the population are homeowners, and I take a sample, and in that sample, 40% of the people in my sample are homeowners, I would have to determine the probability of getting a sample of 40% if 25% were true. If that probability is super small, then I could say that my hypothesis has evidence that the 25% is not true, and I would go from there. Now, if the probability was higher, then I would say, okay, so it's possible the 25% is true. Don't worry, we're going to do all of this with math and all that later. But that's basically what we're doing with hypothesis testing. We're making a claim, we gather evidence, we find out the probability we would get that evidence if the initial idea was true or the information we already had. Okay, here's the steps. I'm not going to ask you to recount these steps. Just kind of want you to know how we do this. So first thing you do is you make a statement. It's usually kind of an educated guess. It's like, oh, I see that there's so many homeowners around me, so I think that it's probably higher than what they have. Then you collect your evidence. I would do my random sample and I would take a whole bunch of evidence, and then I would test the statement. I would analyze the data and determine whether or not it would be plausible to get that data based on what we already know. So this is our hypothesis testing. I'm going to teach you all of the math of number 3. Okay, this is the stuff you're going to need. So our null hypothesis, it's H naught. That's how we would say that. H sub 0 is H naught. So this is what we're testing against. So this is the statement that we are assuming is true until we have evidence that it is not true. So that 25%, this would be my null hypothesis. We assume the 25% is true until we have evidence that it's not true. That's what our null hypothesis is. So that would be that, H naught. The alternative hypothesis, this is what we're trying to find evidence to support. So if I think more than 25% of people own their house, then I would say that my alternative hypothesis is that the number of people who own their homes is greater than 25%. So it's what we're trying to support with our evidence. That's the alternative hypothesis. So here's the different ways that we can write this. So if we have a statement, for example, if I say, I think that the number of people that own their home is different than the 25%. Different could be greater than or less than. It could be either one. Therefore, we would have a two-tailed test. Woo, that was weird. That would be a two-tailed test. If you hear the words in there that it is different than, if you see the word different rather than greater than or equal to, we will have a two-tailed test. Now, if I think that the number of people, the percent of people that own homes is less than 25%, that would be a left-tailed test, because I think that my data is going to lie to the left of, which is less than the 25%. So this would just be less than. And then greater than is to the right because it lies to the right on the curve of that 25%. Wish that I could get rid of this. I don't know how to get rid of this. I wish I could get rid of it. I wonder if I should shove it up here somewhere. I don't know. I'll just shove it up there. It won't get off my screen. Before it would get off my screen, and I don't know what I did to get rid of it previously. So it's just going to kind of live up there. It's not on my iPad, but it's kind of from my iPad. I don't know. I'll figure it out at some point. Okay, let's move on. So our null hypothesis is the status quo. It's no difference. We assume the null hypothesis is true until we have evidence to the contrary. So this right here is the important piece right here. We assume it's true until we have evidence that it is not true. So we assume that 25% of all people, all families are homeowners until we have evidence against that. So I told you, we're flipping through these really fast. All right, so let's talk about what these are right here. And we'll talk about the null and the alternative hypothesis. I hope that I didn't mess this up. Okay, I'm good. All right. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So different, remember, different is a two-tailed test. It's going to be on the next screen also, but I would prefer to kind of talk through it. It's a two-tailed test because it could be greater than or it could be less than, but it's just, we think that researcher thinks it's different. So it's a two-tailed test. So my alternate or my null hypothesis, my H naught, is that our P, our percentage or proportion is equal to 0.62. We always write it as a decimal. So we're going to assume it's 62% until we have evidence to the contrary. My alternative hypothesis, we're doing H1, aren't we? My alternative hypothesis is that P is different, so it's not equal to 0.62. This is what a two-tailed test looks like. So they think it's different. So we just think it's not equal to 0.62. It could be greater than, it could be less than, but we just think it's not equal to. Questions? All right. So this is exactly the same thing as I just said. Null hypothesis, P equals 0.62. Alternative hypothesis does not equal 0.62. I just like writing it. All right, next one. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes the mean length of a call has increased. Has increased, that would translate to greater than, right? That would translate to greater than. Therefore, this is a right-tailed test. Man, my brain. Because he thinks it is increased, he thinks it's bigger than. So if it is bigger than, it's a right-tailed test. My null hypothesis always has an equal sign. He thinks it's the mean equals 3.25. So we're looking at the mean because it says it right here, the mean length of a phone call. So we're looking at the mean, so we'll use mu equals 3.25. My alternative hypothesis, they think it has increased, so we think it's bigger. So it would be mu is greater than 3.25. The number is always the same, just the symbol that changes. The null hypothesis will always have an equal sign. The alternative hypothesis will either have that doesn't equal to, a greater than, or a less than. Questions? All right. Same thing. It shows exactly what I just said. Shows what I just said. I just like to write it. All right, let's go to the next one. The last one of these. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control. Oh my gosh. Yeah, I've had some pretty long phone calls. When I was in high school, I used to fall asleep on the phone with a friend, and then we'd wake up in the morning and we'd both still be on the phone. Yeah, good thing it was free. Yeah. Okay. Quality control manager believes the standard deviation has decreased. These words right here mean less than. That was back in the days before cell phones, though. I had this really pretty princess rotary phone in my room when I was a kid, when I was a teenager. All right. So 0.23 ounces was our standard deviation. We think it is less than, so this is a left-tailed test. Because it's less than, we think it's to the left. So my null hypothesis is the standard deviation, so sigma equals 0.23. Because it's standard deviation, 0.23. And then our alternative hypothesis, we think it is decreased, therefore it is less than. There we go. Questions? Okay, this is just the exact same thing. I'm just like to write it down. So it's all the same stuff. Plus, if you print out the PowerPoints, it's probably good that that's already written there. It's better than my handwriting. Might be better than your handwriting. I don't know. I mean, the only thing I see is in your work and on your hand in homework, and it's not necessarily what your homeworks or what your handwriting really looks like. All right. Questions before we move on with the null and the alternative hypothesis? This is basically mostly what the 10.1 homework is, mostly determining your null and your alternative hypothesis. All right. Okay. So here's the four different outcomes we can have of hypothesis testing. So the two good ones, these are the two good ones. We reject the null hypothesis when we have enough evidence to show that our alternative hypothesis is true. This is a good decision. If the alternative hypothesis is true, then we'd have to reject the null. We fail to reject. I don't use do not reject. I use fail to reject. We fail to reject the null hypothesis when it is true. This is also a good decision. So if we don't have evidence to show that the null hypothesis isn't true, or to show our alternative hypothesis is true, then we would fail to reject. So if I ended up with a probability that was pretty large, like, I don't know, 25, 30% probability of getting our sample, if the null hypothesis was true, we'd fail to reject it. This is good. So these are the two errors that we have. I am pretty lenient on these. As long as you answer them and do the best you can, I'm pretty lenient on the errors. Just do the best you can, put it in your notes. So type 1 error is if I reject the null hypothesis, but it turns out that null hypothesis is actually true. So if I reject the null hypothesis, but the null hypothesis is true, this is a type 1 error. This is not an okay decision. So when you reject it, but you shouldn't, type 1 error. Type 2 error is when you don't reject it, but you should have rejected it. So the alternative hypothesis turns out to be true, but you didn't reject the null. This is a type 2 error. There will be a couple of questions, I believe, in the homework, and there might be one on the quiz. I can't remember. I believe there might be one on the quiz. So keep this in your notes, pay attention to this. As long as you do the best you can, do a decent job of it, read your notes, you should be fine. I'm pretty lenient on these because I always forget which is which. So, but you have it in your notes and you're allowed to use your notes, so you should be able to get it. All right. Let's talk about what these errors would look like. So remember, type 1 is reject when you shouldn't, and type 2 is don't reject, but you should. So what a type 1 error would look like in letter A is, so type 1, and it's going to be on the next screen, but I'm going to do it anyway. Type 1. I'm actually just going to do the other screen. So what a type 1 error would look like with the volunteer charity work. So if the researcher concludes that the probability or the proportion of Americans is not 62%, but it actually is 62%, that would be a type 1 error. Type 2 error would be if the researcher says it is 62% when it isn't 62%. So you see here, it leads to the researcher to believe that it is still 62% when in fact that percentage differs. Type 1 error is he concludes that it does not equal, but it is currently 62%. So that's a type 1 error. Let's take a look at number 2. So type 1 error is have the researcher concludes that that mean is greater than 3.25 minutes, but in fact, the average length of the call is still 3.25 minutes. Type 2 error would be if the researcher fails to reject the hypothesis, but in fact, the average phone call is greater than 3.25 minutes. So he didn't reject it, but he should have. All right. The probability of making a type 1 error is alpha. We have already used alpha. We're going to continue to use alpha. The probability of making a type 1 error is alpha, rejecting the null hypothesis when it is actually true. The probability of making a type 2 error is beta. That is the symbol for beta. And these affect each other. So as the probability of making a type 1 error gets larger, the probability of making a type 2 error gets smaller. You are not required to remember that one is alpha and one is beta. I don't think you're asked that question, but it's here. They do affect each other. So we figure out the probability of making a type 1 error before the sample data is collected. Our level of significance, which is going to be alpha, is our probability of making a type 1 error. You are not going to have to find this. It will be given to you. Your alpha will be given to you, so don't worry. But that is the probability of making the type 1 error. This is my least favorite part of this chapter. Once we're past it, we'll be good. We'll be doing the fun stuff. All right. In other words, as the probability of making a type 1 error increases, type 2 error probability decreases and vice versa. They affect each other. Okay, this is important. We never accept the null hypothesis. Because we don't have access to the entire population, we never accept the null hypothesis. It's just like in court. They say a defendant's not guilty. They don't say they're innocent. It is the same thing. So we say we can either reject or fail to reject. We either reject or fail to reject. We do not accept. We reject or fail to reject. I believe my open math will try to trick you and put an accept in there. Never click on the accept. We don't accept. Okay. All right. Look at that. We're already more than a quarter of the way through. We're doing great. Okay. I'm going to show you what a conclusion is going to look like. So this is the phone call thing again. The sample evidence indicates that the null hypothesis should be rejected. Here's the wording of the conclusion. This is a whole lot of words. The statement in the alternative hypothesis is that the mean call length is greater than 3.25 minutes. Since the null hypothesis is rejected, there is sufficient evidence to conclude the mean length of a phone call on a cell phone is greater than 3.25 minutes. This is very, very wordy. I would probably say something like, there is sufficient evidence that the mean length of a phone call is greater than 3.25 minutes. Therefore, we reject the null hypothesis or reject H sub O. That's all I would say. I would not type out that big paragraph up there. That's what I would say right there. And that's completely adequate. Questions? All right. So let's do another one. So this is the phone call again. The sample evidence indicates that the null hypothesis should not be rejected. State the wording of the conclusion. They give you another paragraph again. I would just say there is not sufficient evidence. Evidence to indicate the mean phone call length is greater than 3.25 minutes. Therefore, we fail to reject the null hypothesis. That's probably what I would write. I mean, if you want to write the big paragraph up there, that's fine. No matter what, it's wordy. This is just the way it is. All right, questions? All right. We're almost to the math. We are now in 10.2. If you keep track of that sort of thing, we are currently in 10.2. You have enough to do the first assignment. And we're going to be like whipping through probably the next 10 slides and then start doing math. So we're good. Okay. So we got a random sample from 1,000 people. They found 534 were in favor of banning cell phone use while driving. So we're trying to figure out, does this suggest that more than 50% of the people favor this policy? Or is it possible that that the true proportion could be less than 0.5 and we just happen to get a good survey? Would it be unusual to obtain a sample proportion of 0.534 or higher if it was actually 0.5? How do we know? Let's take a look. So if something is statistically significant, so if we have statistically significant results, so for example, if the probability was like 1.5% chance, then that would be statistically significant. You're not going to have to remember those words. It would be statistically significant if we ended up with a super small probability. If that probability is less than our alpha, then it is statistically significant and we reject the null hypothesis. But I'm not going to require you to remember that word. It's just there and it is what it is. So I'm calculating my probability here. So this is my standard deviation. And we would do all of our normal stuff. Let me find the probability. So let me see here. One standard deviation away, is that what that is? So we have within one standard deviation, this is my sampling distribution. And then I would say, okay, so let's get 2 standard deviations away. And I can't. So let's get 2 standard deviations away. So I want to know, is it possible that it is greater than? Is it possible that we're greater than 50%? So we try to determine what is the probability that our sample proportion, So we take our evidence and we find out, given that we believe that 50% is the number of people that want to ban cell phones while driving, how many standard deviations away can we be and still be okay? So basically what we're doing is we're going to be creating a confidence interval. And if the percent that I have, my sample, lands outside of that confidence interval, then we can reject the null hypothesis. That's essentially what we're doing here. So we have 2 different ways to look at that. We can use a test statistic, which is like a z-score, or we could use a probability. That's basically what's happening. So what this says is, if our sample evidence is too many standard deviations away from the mean, then we can reject the null hypothesis. So we would compare a test statistic or a z-score based on our sample with the edge of our confidence interval. Don't worry, we're going to math it out and it'll make sense. So right here, I got a z-score with my sample of 2.15. This is more than 2 standard deviations away from the mean. And so we're just using that just because I haven't calculated his confidence interval. This is 2.15 standard deviations away from the mean. Our confidence interval goes to 2 standard deviations away from the mean. Because we're outside of that confidence interval, we would reject the null hypothesis. This is one approach. This is what I would call a test statistic. I don't know what just happened there. This right here is my test statistic. That's what that is right there. All right. So the other way to do this is to find the probability. So the probability of getting that z-score, if my null hypothesis is true, is right here. That is a pretty small probability, and it's smaller than this alpha of 5% that I just now made up. Therefore, that would also cause us to reject the null. So sometimes they're going to have you look at the probability, which we call a p-value. Sometimes they're going to have you look at the test statistic. They're based on the same thing. So don't worry. We'll show you both ways. And I'll show you fancy calculator functions. Where is my calculator? Here it is. Okay. Let's take a look. We already just did that. All right. So the classic approach is to determine if something's too many standard deviations away from the mean, causes us to reject the null. The p-value approach is to determine the probability of getting that, given that the null hypothesis is true. So p-value is just a probability, and test statistic is a z-score. I know this is a lot right now. Once we start doing the math, it's going to make sense. I'm just talking right now to talk. So, all right, I'm going to move on so that we can just get to the math. Okay. And it's going to help once we get to the math. All right, let's move on. Let's move on. We have the same thing like 3 times. No wonder it's so big. I don't know why I have the same, there we go. No. Okay, what the heck? All right. We're still in 10.2. We just jumped ahead. All right. I don't know why I had the same slides like 8 times. Okay, so just a reminder, our p hat, which is our point estimate, is the number of successes divided by the number of trials, or the sample size in our sample. So it's the number of successes divided by the sample size. So this is our p hat. We're going to use the p hat in this section. So also remember, this right here is the standard deviation of our sampling distribution. Because we don't have information about our population, we're going to use this right here. We're going to use this standard deviation. These are the requirements you're going to need to satisfy. So a long, long time from now, like next Tuesday, when the test opens, you're going to have to list all of the steps of your hypothesis testing. I want you to show me these things. These are part of it. So when I ask you to show me every step of your hypothesis test, I want you to do these pieces. So this right here, this independent of each other, this is the, our sample is less than 5% of our population. That's what that means. That's how we know they're independent. And this right here, this tells us it's normal. So these are the three things you're going to test. So make sure that that's part of your hypothesis testing. Okay. When you get a situation, the first thing you do is you determine your null and alternative hypothesis. In 10.2, everything's going to start with P. If it's not equal to, that's a two-tailed test. If it's left-tailed, it'll be less than. If it's right-tailed, it'll be greater than. Our P naught is the assumed value of our population proportion. So that's our step 1. Second step, we'll be given a level of significance. And I'm just going to write given, because you are not going to have to choose this on your own. Now, if you decide to do a hypothesis test yourself, you can just choose your own alpha. So if you decide to do one with your final project, just choose an alpha, pick something. 5% is good. So just choose whatever alpha you'd like if you decide to do one for your final project. I've had a few people do them and they usually turn out pretty well. Compute your test statistic. This is the z-score based on your sample. This is not the critical value we use to create our confidence interval. This is the z-score based on your sample. That's what this is. So you would take your sample statistic, your p hat, minus the given probability, and then you would use the standard deviation using the given. Remember, we assume that the original proportion is true until we have evidence it isn't. And then the last thing you're going to do is you're going to find your critical value. I'm going to show you on the tables how to get those, also using inverse norm as your friend. Inverse norm is also your friend. But important, on a two-tailed test, you use the z sub alpha divided by 2, because this is a two-sided, our alpha has to be cut in half because it's two-tailed. For a left-tailed test, you're going to use that critical value, but it's going to be negative. On a right-tailed test, you'll use the critical value, but it's going to be positive. We don't divide alpha in half for left-tailed or right-tailed tests. You only divide it in half for two-tailed. Questions before we start mathing? Once I start doing math, everything makes more sense. Okay, so then we compare our critical value. Don't worry about this. It's going to make more sense. I'm not going to talk through this because it doesn't make sense without numbers. And then we compute our test statistic. or you get your p-value. We're going to use the computer or the calculator for the p-values. Okay. If your p-value is less than your alpha, you reject the null hypothesis. Oh, sorry. This is the one we already had, but you can write it down again. Okay, good. Sorry, I'm moving too fast. So my high school students love this. If the P is low, reject the hoe. High school kids, this is how they remember it. If the P is low, reject the hoe. So there you go. It works, though. It works. If you remember that in your head, if the P is low, reject the hoe, it will totally help you. They never say the words null hypothesis ever. Even vocabulary, they never say it. All right. Okay, we're going to actually math it out now. But first, wait, hold on. Let me go to my Z table. At the bottom of your Z table, so nice, there's not as much lag on this new computer. On the bottom of your Z table, this is that first page, the Z table, we have our hypothesis test and critical values. These are the most common levels of significance. They're the most common alphas. And it gives you, if you have a left-tailed, a right-tailed, or a two-tailed. So it gives you these. These are the most common. So at the bottom of your Z table, this is just right here for you. You don't even have to inverse T. You don't have to look anything up. It is right there. And it is cool. All right. Okay. In 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 Americans nationwide, 525 stated they did not trust the media. At an alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? Has increased. That's greater than. Greater than, is that a left-tailed, right-tailed, or two-tailed test? This is a right-tailed because it's greater than. Okay. So all the stuff is on the next page. So just letting you know. But 1,010 Americans or 1,010 adults is definitely less than 5% of the entire population. We are going to assume, so if it doesn't say that it is randomly selected, just write down, we assume that it's a random sample. So I'm just going to assume that this is a random sample. Now my NP times 1 minus P. So NP times 1 minus P is greater than or equal to 10. So I have my N is 1,010 times 0.46, 0.54. Here's my calculator. I mean, I know that it's greater than or equal to 10, but this is 250. So that is greater than or equal to 10. Okay, I've checked all my pieces. So now I'm going to start with my, I'm going to do my hypothesis test. All right. So alpha equals 0.05, and this is a right-tailed test. So my critical value, 0.05, right-tailed test, my critical value is 1.645. So I'm going to write that down. That is my critical value. All right. So I got that. Now what I need to determine, I need to calculate my test statistic. My test statistic. Oh, what I need before this though, just a second. I need my p hat. I'm going to put that over here. P hat is 525 divided by 1010. It's approximately 0.52. Okay. So I'm going to calculate my test statistic. This is a z-score. So the test statistic is z equals 0.52 minus 0.46, which is our p naught, so it's that initial value, divided by square root of 0.46 times 1 minus 0.46 divided by, it's just divided by n, right? Divided by n, which is 1010. So I'm just going to put this whole thing in my calculator. I'm going to be really kind with my parentheses. So I'm going to put parentheses around the top. Divided by square root of parentheses 0.46 times 0.54 divided by 1010. That seems really big. Is that what they got? Oops. That seems really big. Is that what they got? Yeah, that's what they got. Okay, that just seemed really large. Okay, it's about 3.83. That is really huge. Okay, so my test statistic is 3.83. That is really huge. So this right here is greater than this right here. Therefore, I would reject the null hypothesis. Let me draw it. So my mean is 0.46. My confidence interval ends right about here. This would be the z-score of 1.645. This is my z equals. That would be this value right here. My test statistic lands me way out here. This is the z equals 3.83. Because that z-score for my test statistic is significantly greater than the 1.645, I can reject the null hypothesis, which I didn't even write down. That was a big faux pas. I apologize. I should have written this first. So I have sufficient evidence to show that the number of Americans who do not trust the media is greater than 46%. Therefore, I reject the null hypothesis. Questions about this before I show you it all just on the screen? We're going to do the p-value also, but just hold off on that for now. All right. So this was all the stuff that I just did before. It's a simple random sample. NP times 1 minus P is greater than 10, and the sample size is less than 5%. Therefore, we can call it independent. So here's my math. My test statistic was 3.83. This is the same math I just did. We have a significance level of 0.05, and we have our null and alternative hypothesis. Here's the conclusion. Here's the good part. It's a right-tailed test, and my critical value, we had 1.645. Since the test statistic is greater than the critical value, we reject the null hypothesis. So one way to look at this, so take a look here. I had my, if I was looking at a z-score of 3.8, it's not even on here. It's not even on here. So and I'm looking at greater than, so I'd be 1 minus whatever I have here. So it's practically zero. The probability is practically zero. So a probability of practically zero is definitely less than 0.05. Our p-value is less than the level of significance. We will reject the null hypothesis. Since a p-value of 3.83, basically zero. So the probability of getting a z-score of 3.83 is basically zero. So we reject the null hypothesis. We're going to do more, don't worry. Questions on this? We definitely need a calculator function. Is it on the next screen? Whoops. So here's my conclusion. There's sufficient evidence at the 0.05 level of significance to conclude that the percentage of Americans that don't trust the media has increased since 1997. We would reject the null hypothesis. Make sure you put those words then. Put the words in there. I want to see on your test, I want to see the words reject the null hypothesis or fail to reject the null hypothesis. And I don't care if you put H sub O or whatever, either way is fine, but I want it to be clear that you are rejecting or failing to reject. Let's do a calculator function. It's not there. Let's do a calculator function. Where am I? There I am. Okay. So in your calculator, it's second. No, it's not. It is stat tests. And it is one prop z test, one proportion z test. This is your calculator function. I'm going to write this down on my iPad also. One prop z test. That is the calculator function we're looking at. My P naught was 0.46. Make sure you turn it into a decimal. My number of successes was 525. My sample size was 1010. Now, 99 times out of 100, I choose the wrong one of these. You know you've chosen the wrong one if you end up with a super large probability. And I think it's supposed to be this one right here. If I ended up with like a 99 or 0.9999 probability, I chose the wrong one. So you choose whether it's right-tailed, left-tailed, or two-tailed. See, I chose the wrong one. I do that every time because I ended up with a super large probability. I chose the wrong one. So you can either just do 1 minus that number or just redo it and fix it. I do it all the time. All right. So notice this number here, 6.858 times e to the -5. If I move my decimal place 5 to the left, I'm going to write this down because I can. My p-value, 0.1234689. And my z-score, the reason the z-score is slightly different is because of rounding, but it's okay. It's still greater than 3.8. So it is definitely, we would reject the null. Questions on the calculator function? So this z-score right here is your test statistic. It will not give you a critical value. You need to find that on the either on the z-table or using inverse norm. You need to find that yourself. It gives you the test statistic and it gives you the p-value. So this was my p-value. That might as well be 0. It's way less than 1%. Question on proportions. We're going to do means next. Okay. Let's take a look at means. We're in section 10.3. See, look at this. It's only 6:30. We're in 10.3. Y'all are awesome. All right. So once again, when we're dealing with means, we are once again going to use t-values. We're going to use t-values for our critical values. Just like we did previously, we're going to use those t-values. This right here, this is your test statistic. Which is just I like to say Z, kind of a Z-score, but it's with sample data. So it is what it is, but it's the same thing we did before. It is finding that Z-score based on the data that you have. So we are using a T distribution. So technically it's a T-score, but whatever. And your critical values will be n-1 degrees of freedom. Just like we did in last section or last thing. Remember that T distributions are different for different degrees of freedom. So we need to use our sample size to determine that. Area under the curve is 1. This is all the same stuff. It's all the same stuff. All the same stuff. All right. When we are testing our hypothesis regarding population mean, once again, we need a simple random sample. You either have a normally distributed population or your sample size is greater than or equal to 30. Sample size independent of each other. This is that the sample is less than or equal to 5%. Actually, it's less than. We don't need the equal. It's less than 5% of the population. So once again, make sure you show these things to me when you are doing your hypothesis test on your test. Okay. We're going to be using mu. We're not going to do any standard deviation ones. We're going to be using mu. So when it is one dealing with mean, once again, two-tailed test is a not equals to, left tail is less than, right tailed is greater than. Y'all are like extra quiet tonight. You're riveted. That's what it is. You are riveted. Okay. So you're going to be given a level of significance. Then you test your test, you compute the test statistic. So once again, we use n-1 degrees of freedom for our critical value. Same thing before. The critical region, and I didn't mention this before, the critical region is the region that would make you reject the null hypothesis. I believe in the homework, it asks if something lands in the critical region. If it is out here in these shaded areas, if it is lands out here or out here, this is the critical region. If it lands in the outside of your confidence interval, it is in the critical region. So if it asks you about that, that's what it means. Critical region is the area that would cause you to reject the null. Compare your critical value with your test statistic, and that will get you either rejecting or failing to reject. It says use table 6 to approximate your p-value, but use the calculator. Just use the calculator. If you're somebody that calculates things by hand and uses tables, just take the loss here and just use your calculator. So much more accurate. Your calculator is going to give you a p-value that is liked more by my open math. So just use your calculator. Okay. We already did this. Let's math it out. Once again, if my p-value is less than alpha, reject the null. The p is low, reject the ho. Then you state your conclusion. Let's math. Okay, I don't care about that. All right. We are assuming the resting metabolic rate of healthy males in complete science is 5,710 kilojoules a day. The researcher measured the RMR of 45 healthy males who were listening to calm classical music, found their mean to be this, and the standard deviation to be this, at a and alpha equals 0.05 level of significance, is there evidence to conclude that the mean RMR of males listening to classical music is different than 5710 kilojoules a day? So different than, that indicates a two-tailed test. This indicates a two-tailed test. Therefore, we will cut the alpha in half when we are looking for our critical value. So we'll cut that in half because we're going to use T sub alpha divided by 2 for our critical value. You can use the table or you can use inverse T. Since I have 45 right here, I would say use inverse T. So I'm going to go back here, not right there. I'm going to go this way. Second vars, inverse T. Remember, we're cutting it in half. So I do 0.025. Degrees of freedom is 44 because my sample size is 45. And I'm going to get a critical value. So it'll be plus or minus, because either positive or negative. 2.02, we'll go with that. Okay, so I have my critical value. I'm going to write my null in my alternative hypothesis. So my null hypothesis is that the mu equals 5710 kilojoules per day. My alternative hypothesis is that mu does not equal 5710. So what I'm going to look for is is my test statistic greater than 2.02 or less than negative 2.02? Is it one direction or the other away from this? All right. So all the things I would test, if my sample size is greater than 30, therefore we have normal. 45 healthy males, that is definitely less than 5% of the population. And yeah, and we're assuming simple random sample. Okay, let's math. So my test statistic is going to be my sample 5708.07 minus what they gave me, 5710, divided by my standard deviation, which would be 992.05, divided by the square root of 45. Parentheses are your friend when you're putting this in your calculator. 5708.07 minus 5710 divided by 992.05. I used parentheses for that, divided by the square root of 45. Closing my parentheses, getting out of that first. So I have my test statistic is approximately negative 0.013. Okay, my test statistic is greater than negative 2.02. So if I drew my confidence interval, this is negative 2.02. This is 2.02. These are the z-scores. My test statistic is right about here. This is negative 0.013. It is not inside the critical region. We would reject if it landed out here or out here, but it's not out there. It's inside the happy place. I'm going to make it pink because it's happy. This is the happy place. If it lands in there, then what we have is not unusual. Our sample is not unusual enough. We don't have sufficient evidence to reject the null hypothesis, so we are going to fail to reject. Questions before I Go to the next page. Okay. So take a look right here. So my, hold on a second here. I'm not on the, what am I doing? Okay, here's my math. So we did our null and our alternative hypothesis. Our significance level was alpha equals 0.05. The sample mean, we have all of that. And here's the math that we did to get the negative 0.013. So we got the negative 2.021 and positive 2.021. My test statistic is in between those two values. So I failed to reject the null hypothesis. I'm going to show you how to do this on the calculator in a minute. So by hand, it's not exact. We're going to use the t-test function. So let's go to the calculator. Let's go to the calculator. Whoops. All right, let's do this calculator stuff. So go hit stat, arrow over to tests. We want t-test, which is the second one right here. Once again, just like when we were doing confidence intervals, if you have the data, so if they give you a list of raw data, you would put it into your L1 and then use that, but we were given stats. So I have that my null hypothesis, 5710. Remember, anything that has a sub-zero, that's like your initial value or what you're proving. My X bar, that is the sample mean, 5708.07. My sample standard deviation they gave me, 992.05. I can my sample size, that's important, 45. Okay. The not equals, I always get that one right. I always get the not equals one right. That's, like, never get that one wrong. Let's go to calculate. My p-value is 0.9896. That is a huge p-value. And it gives me the same test statistic that we have. Because this p-value is greater than my alpha of 0.05, we can fail to reject the null hypothesis. Are there questions? Y'all are being extra quiet tonight. All right. We are almost there, guys. We're almost there. So I was already back there. There's insufficient evidence at alpha equals 0.05 to conclude that the mean RMR is different from the 5710. So write the words, fail to reject. Fail to reject. I want to see those words. Please write fail to reject or reject. We fail to reject. Okay. So in this one, we were given data. You are given data here, and we're going to use our calculator. So what we want to know is, so this is the weight of 18 state quarters, and they were weighed. The mean weight according to the US Mint is 5.67. What I'm trying to determine is if they have a weight different. This is another two-tailed test. Are they different? So based on my data, is it different? Did we do the math in here? Okay, we're gonna just a moment. Okay, so our significance level is 0.05 again. We are trying to determine whether the weight is different. So let's go here. We are assuming the weight of 5.67 grams. This is a two-tailed test because we have the word differs. So this is a two-tailed test. Our sample size is small. So the way that we can determine is if the population is normal. Let me see here. Does it tell me that they're normally distributed? It doesn't tell me they're normally distributed. So what we would do is we would graph it. I'm not going to require you to do this, but this is what somebody would, if this is what would be done in the real world, because we have a small sample size, we would graph it. And if it looks normal, if nothing's too wild and crazy from this line of best fit here, we can say it's basically normal. You can also use a box plot. You can use a histogram. If you graph the data and it appears normal, then you can just say it is normal. We are just going to assume it's normal. If you go further in stats, take 244, for example, they'll go a little bit deeper into this. Okay. Yep. See, here's my box plot. My box plot shows that it is basically normal. So we're good. That there's no outliers. Okay. So I'm going to go into my calculator and we're going to do this with the data in the calculator. So let's go into the calculator, go into your stat and into your edit into L1. I'm going to go back to get my data. I'm just going to put this data into the L1. Uh-oh, I did something weird. Let's try this again. Because I hit the comma instead of the point. So I'm just entering all of this state quarter data into my L1 here. Okay, 5.73. Oh, that should be a 9. Having a lot of the same ones is messing me up. Okay, sample size right? Yes. Give you a second if you're putting it in yours as well. Get you a second to catch up. All right, so before we do all of this, I'm going to go back to my other screen. Okay. So the null hypothesis is that the mean is 5.67. The alternative hypothesis is that the mean is not 5.67. We have a significance level of 0.05. So I'm going to get the, before I gotta quit doing that. Before I use my calculator to analyze this, I'm going to get my critical value. So I'm going to go to second vars and I'm going to go to inverse T. It's a two-tailed test, so we're still doing 0.025. And we have 18 is our sample size, so I'm going to use 17. Don't forget to subtract 1 from your degrees of freedom. Hit enter. That's not where I want that. The heck did I just do? I don't know. There we go. I need to delete that. Delete. That wasn't supposed to go there. Okay, get out of there. Man, I am losing my brain. It happens occasionally. Don't get old. All right. It's all still in there. All right. So my critical value is going to be plus or minus 2.1098. So in order to fail to reject, I have to be in between negative 2.1098 and positive 2.1098. So that's where I'm trying to land if I want to fail to reject. So let's go back to stat and tests. T-test is where we want to be. And then I have data. The thing about this is what it doesn't know what our null hypothesis is. So I have to put that in there. 5.67. It doesn't know the null hypothesis. It does know the list. I have the list right there. So L1 will give us our data. And once again, it's not equal to. Hit calculate. So I have a test statistic of 2.75. And I have a p-value of 0.01. So my alpha was 0.05. This p-value is less than that 0.05. That would cause me to reject the null hypothesis. Plus this 2.75 t-value right here is greater than our critical value of 2.1098. That would also cause me to reject the null hypothesis. So go back to my page. So I'm going to draw the curve. So my critical values are out here, negative 2.1098 and 2.1098. My test statistic landed me right here. 2.75 is about out there. It is in that critical region. Therefore, I would have to reject the null hypothesis. Remember, the p-value says that the probability of getting this particular value of a sample, given that the null hypothesis is true, is, what was that? It's less than 2%. So the probability of getting a sample like that, if my null hypothesis was true, is less than 2%. Therefore, it's unusual. Therefore, I reject the null hypothesis. Questions? So here's my conclusions. Since the test statistic is greater than the critical value of 2.11, we reject the null hypothesis. Or you can say, since the p-value is less than the level of significance, we reject the null hypothesis. Use your calculator. Please use your calculator. That's it. There's sufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean weight of state quarters differs from 5.67 grams. Write the words, reject the null hypothesis. That is my last slide. My last slide. So, questions about today's lesson? This is a good time for that. Does anyone have questions?
No, I think I'm gonna kind of have to listen to the videos over again to kind of put it all in, like group it all together.
I know it's a lot. I'm so sorry that I gave you guys so much on one night.
But I think, like I said, I think for me, it's more like the vocabulary. When I can kind of get the vocabulary figured out, then it helps out.
Yeah, it makes sense. Absolutely. Yes. Yes, reject the hoe. If the if the P is low, reject the hoe. You guys are going to remember that. You know, if you don't remember anything else from this class, years from now, you're going to be, somebody's going to say something is low and you're going to think if the P is low, reject the hoe. It's helpful. Yes, this was a lot. I'm so sorry. So yeah, if you can parse this together, maybe, you know, can you know that you want crocheted mushrooms. All right. All right. So yeah, digest it, ask questions. I will check my messages and everything as frequently as I possibly can, because it's like Thursday night from, 5 o'clock until basically 5 o'clock on. I won't be available, but the rest of the time I'm totally here for y'all. So any other questions or comments or anything for the video or the recording? I'm going to shut it off if not. Okay. Shut off the recording.